Okay, guys, so there a tree. I've just written down the definition of a tree because we're going to be working with it. It's a connected graph with no circuits. Just a reminder of what a connected graph is. It's a graph where all the vertices are directly or indirectly connected, right? And no circuits. You remember what a circuit is? That's a path, so a route from one vertex to another, but usually going through multiple vertices. But if it starts at one vertex and it goes back to the same starting vertex and it ends there as well, that is a circuit. All right, so in a tree, we don't have that. So I drew two examples there at the bottom, and then hopefully if you link that with the definition, it should make sense. Guys, double check. AB is 12, BC is 15, AC is 10, AD is 5. Then we have CD is 8. I'm also just checking that I filled everything in. CE is 9. AF is 8. Then we have two that are 7 here, DE and AE. CF is 11, CG is 4, and GF is 12. Okay. Now, guys, Kruskal's algorithm, note that they haven't told us which vertex we're supposed to start at or which edge we're supposed to use first. All right. With Kruskal's algorithm, we go and we look for, I want to say the shortest edge, but it's not necessarily shortest, right? Remember, they can put all sorts of things on here. It can be value of money for a ticket, or it can be length, or it can be, yeah, all sorts of things. Okay, so that's why I wrote in this paragraph, Kruskal's algorithm involved choosing the edge with the least weight. All right, so whatever that weight represents, the smallest number, continuously, disregarding those that would create circuits until a spanning tree is found. Now, guys, this is also going to be important. All right. This is almost going to be a bit of a check that we can do. How many vertices do I have here? 1, 2, 3, 4, 5, 6, 7. All right. So this spanning tree should have 6 edges, always one less than the number of vertices. All right. So once we have 6 edges, it's supposed to form a spanning tree. If our 6 edges don't, then we know we've done something wrong. Okay, so that's something that we can keep in mind. And just maybe make a little note there at the top. We're looking for something with 6 edges. Oh, it looks like this pen is on its way out. 6 edges. All right, now guys, which edge here in the whole graph has the lowest or the smallest weight, the least weight? CG. So that's the first one that we're going to choose. Right now, it is quite useful to either go over it in the same pen and make it thicker, or maybe use a highlighter or use a colored pen and just kind of color it in. All right, so that you can kind of follow what you're doing. Yes? Sorry. 7. One, 2, 3, 4, 5, 6, 7. Okay. You made me misty. Sorry, yeah. Fine. All right, so the first one that we have is CG. Oops, C. So let's write that. And I'm just going to write in brackets the weight of CG is 4. Okay, now we've covered the one that's 4. Which edge is the next smallest value? AD, right? The one that's 5. Okay, if I fill in AD, is that going to create a circuit with the CG that I've already chosen? No, right? They're not even connected at all. So it's not a problem. We can choose AD. So that is going to be the next one. We can put a plus here. Now, guys, we don't need to write them in any specific order because it's not going to form a path. All right. It's not like you have to first do CG, then you go here, then you go here, then you go here. With a tree, it's completely different. All right. They are all connected, but probably indirectly. All right. We can't have, no, not probably, definitely indirectly. Okay. So we're not going to ask you for the route that this thing must follow necessarily. We just actually want to know which edges are going to be a part of this tree. Why does it look so skew on? It looks straight on my page. Weird. Okay, anyway. All right, so now we have 5. What is the next edge with the, or the edge with the next least weight? 7. Do we notice that there are 2 with a weight of 7? Now, guys, if the 2, or if both of those edges with the same weight, if we could fill them in without creating a circuit, then we would choose both of them. All right. But now, if I choose, let's say we're going to go, I just want to make sure that I'm following this so that okay, if we choose DE, right, it really doesn't matter actually, but if I choose DE, all right, which is 7, can I now choose AE as well? No, because if I choose AE, it's going to create a circuit, all right? And the definition of a tree is that it is a connected graph with no circuits, okay? Because if we fill in a circuit, guys, it's almost like wasted. All right, it's wasted cost to fill in that AE because A and D and E are already connected. Does that make sense? Right? We don't still have to connect them directly. They can already be connected in that way. All right, so AE, we actually, I see in the textbook, they've turned AE into a dotted line so that we know that it's not going to be a part of the tree. Okay, you obviously can't do that if you've done it in pen. But if it's in pencil, maybe you want to do like a little dotted thing there. So I can, for example, do that. But don't worry if you can't, we'll just not color that one in. Yes. No, so you could have done AE instead of DE. All right, would have had the same effect because it has the same weight. And that's all that we're actually interested in. Okay, so let's fill in plus DE, which is 7. Okay, now after 7, which one comes next? 8. There are 2 of them with a weight of 8, eh? All right, so CD, let's see, can I add CD without creating a circuit? Yes, so let's do that. We are connecting CD. Hey, this pen. All right, and I'm writing here. Oh, that's smudged there. Okay, I'm adding CD to my tree, which is 8. I'm already on 4, hey? I'm supposed to only add 2 more. And then I'm supposed to be done. So let's see, the other one with an edge, or sorry, a weight of 8 was AF. If I add AF in, will that create a circuit with any of my lines that I've already connected, or my edges rather? No, so we can add in AF. Okay, next. 9, right? CE has a weight of 9. Guys, if I connect CE, is that going to make a circuit or create a circuit? If I connect CE, I'm going to have a circuit there, hey? All right, so I'm not going to connect CE at all. So I'm going to just do a little erase vibe here. There we go. So that's what I meant in the summary where I said we disregard any edges that will create circuits. Okay, so that edge CE is not going to be in our tree. All right, the next one would be 10 AC. Is that going to create a circuit? Yes. So we're not going to connect that one. No, you can just connect the ones that are supposed to be connected. Yeah. Yeah, no, don't worry about the erasing thing. Okay, next one would be 11. Is that going to create a circuit? Yes, hey, it's going to make a circuit over there. So as you add more edges, you need to kind of look in a bigger space for the circuit. But do we agree if I fill in this 11, I'm going to have a circuit there, right? So I'm not going to do the 11 one either. Next one would be 12, but now we have two with a weight of 12. Right, the one right at the top and the one right at the bottom. So what do we think? If I fill in GF, is that going to create a circuit? Yeah. Yes, definitely. Okay, so I'm not going to do GF. What about AB? No. All right, so I'm going to do AB. And that would give us 6 edges, which means we are supposed to have a full spanning tree, which we're going to check just now. All right, so plus AB, which is 12. Right, I'm just going to quickly erase this. All right, we have 7 vertices. We're supposed to have 6 edges. We have our 6 edges here. Are all of the vertices connected? If we look at those pink lines now, right, do those lines reach all 7 of the vertices? Yes. All right, so we've done a minimum spanning tree. The reason for why we start from the shortest, all right, the edge with the smallest number on it, the smallest weight, and we work our way up, is so that we get the minimum tree. All right, you can get lots of other trees, but we're looking for the minimum one. Okay, if we're thinking of in terms of cost, for example, maybe this was like the example that they used in the textbook was saying, electric power points at a campsite do not need to be connected to every other power point. As long as every power point is connected to another point that is even indirectly connected to the source, then all power points can be supplied with electricity. Right now, say for example, these weights represent like lengths of the power lines or whatever. Not the power lines, you know what I mean, the leads and stuff. All right, it would obviously be cheaper to have shorter ones. Okay, so that's why we're looking for the minimum one. Okay, does that make sense, guys? Yes.
Would it ever affect the weight of the spanning tree? Like when we chose DE instead of AE, you have a graph where it does affect it, which one you choose?
I wouldn't think so, because after choosing AE, we would go to the 8 anyway, and we would work our way up again. So it might be connected in a different way, but you should have those same edges connected. Okay. All right, now guys, the only thing that's left that we have to do here is we need to actually add these numbers together, because that will give us the total weight of the graph. So just add those numbers together and it should add up to 44. Right? Now they didn't tell us what the unit is here, so let's just say units. Could be 44 rand, 44 meters, 44 whatever. Yeah, but that's not too bad, right? Hey, how do you feel about that? Just starting by choosing the shortest edge, working your way up, and making sure that you don't create circuits. Okay, now guys, we're going to practice using Prim's algorithm on the same picture. All right, so I'm not done drawing it yet, but just underneath, if you have space, you're going to write that method 2, Prim's algorithm, this question, and then we're drawing the exact same picture. Okay, so that we can see how the 2 algorithms will work differently, but we are still going to get 44 at the end. Okay, even if our tree is slightly different, if we have different edges connected, but we will still get 44. Okay, so obviously my picture isn't done yet, but you're copying the picture that you did for the previous one. Okay. Okay, so they told us that we must start at vertex D. Now from vertex D, we now need to choose the edge that is connected. Oh, I didn't fill in this length here. What is this? 8. Apologies. All right, now if we're looking at vertex D, do we agree that there are 3 edges connected to it? we need to choose the edge connected to vertex D that has the least weight. All right, and I'm sure we all can see that that is AD, which is 5. All right, so that is the first one that we're going to choose. So AD. Even though it's not the one with the least weight attached to it in the whole graph. All right, it is the least weight connected to vertex D. So we're choosing AD, which has a weight of 5. Now we have 2 vertices in play. All right, now we're going to choose the shortest. I keep saying shortest, you know what I mean, right? Edge connected to either A or D. All right, now do we agree that in this case, the shortest one connected to A will be AE, which is 7. And the shortest one connected to D, after we've chosen the one with 5, is DE, which again is 7. All right, now in the previous one, we chose DE. Let's choose AE this time. Okay, again, guys, if you could choose both of them without creating a circuit, you would choose both of them. All right, we are deciding to choose AE. It doesn't matter because they have the same weight. So regardless of the one that you choose, it's not going to make a difference to the final outcome. But can I choose DE as well? No, because that's going to create a circuit. Okay, so plus AE, which is 7. Now we're going to look at the 3 vertices that are connected so far, and we're going to look for the shortest edge connected to D or A or E after 7. Okay, because that's where we are now. Not 8, not 10, not 12. Well, it could be 8 possibly. And that 8 there. All right, we have 2 options for 8. Do we see that? All right, will AF work? If I connect AF, will that create a circuit? No, so I can choose that one. What about CD? Will that create a circuit if I add CD? No, so I can add both of them. All right, so CD and AF. Okay, we're on 4. We need 2 more, right? Okay, what next? There's a 9 over here, but is that going to create a circuit if I add in CE? Yes, so I can't add that one. So if you want, you can do something just to show that we can't add that one. All right, that we've already looked at that one, but it's fine if you don't worry. Okay, what next? CG. Oh, sure, I didn't even see that one. CG, obviously that's definitely the shortest one. Hey, that one has 4. Okay, and that's also not going to create a circuit. So let's add that one in. I'm just turning my page so that I can do my color. Yeah.
So if they're the same weight, do we always do both of them?
Unless one of them creates a circuit, which is what happened with the 7.
Yeah.
So then you would choose whichever one you want and then just go from there. But if you can add both of them, you would add both.
What if the one of the 8s is connected to like some super low weight things like 2 and 4, and the other one is really high weight things like that?
Well, then the other high weight one, look, you wouldn't connect later on. Because you see what happened now. We chose DC, and that is getting me to the 4 anyway. But it's almost like the shortest way of getting to F, because I have to connect F to the tree, would be by connecting the 8. You see? All right, we're nearly done. Guys, what is the next one that we need to do? Can we notice that we only still need to connect B to this tree? Right? We've connected all of the other vertices already. So what are we going to do for that? AB, right? That's the shortest way of getting to B. All right, if we're looking at the vertices that are already connected, it's either going via 15 or going via 12. And guys, we can't do 10 because that will create a circuit. All right, so we're going to go via AB. And then that should be it. And now we add all of those numbers together. And what do we get? 5 plus 7 is 12. That's 20, 28. 32 plus 12 is 44. Okay. Now our tree is slightly different from the one that we got in the first example. And the only reason for that, actually, in this case, it's not because we've used a different algorithm. It's because we made a different choice. In the first example, we chose DE, right? In order to get to vertex E. In the second example, we chose AE in order to get to vertex E. But because they were the same weight, it didn't actually change the value. Okay, how are we feeling? All right. Okay, guys, let me just quickly see. That's basically what I had planned for today. And it is 2 minutes past 4. Let me just quickly check here. I do want you also just to practice it because tomorrow we're going to do something new. And I don't want to do something new until you haven't practiced this, all right? So until you have practiced it, cheapers, before you haven't practiced it. It's been a long day. Okay, so exercise GT 6.1, which is on page GT, goodness, 0.25. Answer series always has the weirdest way of numbering their pages. I would like you to do number 2, which is just like the one that we've done now, where they give you the same graph and they say find a minimum spanning tree using Kruskal's, and then the next question using Prim's. Okay? Yes. No, so for graph theory, they always give you, so like I also normally do in test or exams, we give you like printed versions on like answer sheets and so on, and you would work on them.
Going in line with the fact that you just do it for your own sake, it wouldn't actually look for the line.
Yeah, I think it would be for your own sake, yes. I mean, I haven't marked final AP exams, but this is what they would mark, I'm guessing. So it is important to write that as well. But guys, do we agree that it helps if you actually do the coloring in of the edges as you go? All right, I don't know if you guys have this book. I'm not sure. So I'm just going to put the question on the board. So that is 2A and B. You maybe just want to take a picture of that. And then you can work on it now here if you want. I'm going to sit here until 4:15. Or if you are itching to get out of here, then you can. I saw Ahmed like, why are you putting it on the board, man?